Well, greetings. Doing a little experiment here with a uh, PowerPoint presentation to see if we can do a good job of having a presentation strictly online. The topic today is groundwater and well field management, primarily operated toward water well contractors for water operators. The purpose of this presentation is an introduction for practical operational leaders on groundwater occurrence, movement, protection for groundwater source systems, and considering groundwater and watershed protection and management, how to locate well fields and protect the ones you have, maintain and enhance recharge, avoid contamination of groundwater supplies, and account for natural water quality issues in daily operations. And last but not least, to operate wells sustainably. Groundwater has a lot of advantages as a water source. It is relatively, but must make the point, that is not absolutely more protected from contamination, especially the more pathogenic types. The chemistry is relatively stable. This has been understood for a long time. It's easier to design water treatment around these. It's much more predictable and requiring less day-to-day adjustment. Turbidity and microbial content are usually much less than surface water, except in situations where wells are basically need cleaning, as we'll talk about. And aquifers are far bigger than constructed reservoirs by a long shot. The mass of groundwater available, for example, in Ohio or the United States, is much bigger than the corresponding surface water. Looking at Ohio, we have a number of aquifers in Ohio. It's sometimes understood to be not a very exciting state, but actually it's pretty interesting. But this can boil down to three types of aquifers. There's the carbonate aquifers. These are the limestones, dolomites, similar rocks, largely found in Western Ohio, but not exclusively. Sandstones and shales prevail more in the eastern part of the state. In the south, we have poor development of aquifers in the bedrock. The last part of it is because of our glacial heritage, we have quite a few sand and gravel aquifers. These correspond to river valleys, including the entire Ohio River Valley system, as well as tributaries into it, most prominently the Miami River Valley system, the Scioto, the Licking, the Muskingum, and then up in the headwaters, definitely very important systems, and more of a sheet sand and gravel situation in the far northwest part of the state. Typical Ohio is going to be a situation like bedrock plus sand and gravel terrace, which is usually developed along an old valley system, for example, outwash from a glacier that was from the past. And the sand and gravel aquifers are being recharged by the bedrock around them. In some cases, some of the bedrock is more like bathtub and contributes very little. But these can be rather complex to test and model. Another way to look at aquifers is whether they're unconfined or confined or not. An unconfined aquifer has a water level within the aquifer, which is pulled down by a pumping well. The confined aquifer configuration, the water level is above the top of the aquifer, usually encountered in a well above the formation where the water is occurring. That's known as the aquifer. River valley aquifers, they may be multi-layered, maybe have an unconfined layer and then a confined layer, or partially confined or leaky confined. There's no either or in some of these situations. Now for something completely different, I work in Tanzania. Actually, I own a well construction company there along with a partner there. And in our home city there of Dodoma, Tanzania, the Makutupora Valley is it is a Rift Valley seismic feature. And in this case, what you're looking for is the Rift Valley aluminum stores water from the rainy season, and the well yield is actually from the rock fractures below the valley. So the wells are cased down into the fractured rock situation, but the river valley itself provides, think of a sponge that is slowly drained over the dry season and then replenished during the rainy season. Just a different way that something like that might occur. Let's look at water well design, construction, and testing. There are limits to everything, and even a stupendously productive Ohio glacial alluvial aquifer, we have to manage them rationally and not every person for themselves. That is, we have to start thinking about agriculture and towns and various towns and other users like that, thinking more of a productive management approach. I'm just putting this at the largest level. We also have to think about what we do over our aquifer systems. For example, this location in southern Ohio, the only flat land happens to also be on top of the aquifer. And so there's oil and gas activity, there's gas stations and everything else right beside productive water supplies. Now, ground sources as water supplies, a lot of things are needed. We need to have sufficient permeability and storage to supply water to the wells. There needs to be sufficient recharge to replenish the water extracted for water supply. In Ohio, neither of these are typically limiting, but we do find that in Tanzania. You might have the permeability and a very nice sand, but no way to supply recharge to it. There needs to be an absence of some kind of deal killer water quality parameters, such as, for example, excessive uranium, which you find in shales. And there needs to be protection of the resource for the long term. There needs to be science to understand the appropriate extractive design and not overdrafting, and calculated over the long term. And finally, engineering and craft, wells and assets built for the long term. We recommend geologist-led test drilling, provides the best information for these things. There's a lot of engineers and towns, they go straight to the water well contractors, and we greatly respect our water well contractor colleagues, but they don't always have either the assets, the time, or the inclination to be your hydrogeologist in addition to being the people that craft your water supply. They've got other things to do with their equipment and with their time. Hydrogeologists such as ourselves really focus on the science and providing the information that you need. And with the water well contractors and the consultants, hydrogeologists such as ourselves and the engineers working in cooperation, contributing that part of the asset set that gets the job done. Together, you have a great package. A feature that's seldom used in Ohio, but well used elsewhere in the United States and in Tanzania is geophysics. Geophysics is a series of methods that provide relatively rapid, cost-effective site recon of a site. For example, you have a large cornfield somewhere, maybe 40 or 50 acres, and you're trying to figure out whether it's going to be a suitable groundwater supply or not. You can go over it with the geophysical methods, see if there's permeable formations present, pick drilling targets. That way you're cutting down on random drilling and weeks of costly drilling and practice. Or if it's not going to work out, you can walk away without the expense. This definitely requires expert guidance and performance. You have to have geophysicists to do it. I am not a geophysicist. I use the information as a hydrogeologist to develop a water supply, but I do rely on people that are actually experts in this process, such as these guys in Tanzania. One thing hydrogeologists can do from water quality, we can predict water quality changes that are going to affect your water treatment design using on-site methods. This is something we can do in the field, and I must say we're usually right. We can predict mechanisms that are going to degrade your performance. We can also give you the timing of it. Generally, when we say that you're going to be cleaning wells in 3 years, you probably should plan accordingly. This comes from long and bitter experience. Construction and contractor standards. What we're looking for, everything is expensive. It keeps getting more expensive, but all of us together, the engineers, the users, the contractors, what are we doing? Are we installing a lifetime potable water supply or a hole in the ground? Standards and specifications, there are many. These ensure that proper materials and methods, and they're usually very specific. In the case of Ohio, there are rules on water supply and construction, and they're very specific. Inspections, something, for example, that hydrogeologists provide, assure that meeting the specifications is good practice. The problem with wells is that they are 95, 98%, maybe even 99% or more in the ground and out of sight and difficult to inspect. So you sort of have to watch them going in, and you have to know good practice. There need to be good specifications. And something we like to do is kind of pre-select who is working on our projects. Communication. Every groundwater project is different. Generally, you encounter things that you didn't know you were going to encounter when you get there. And so that's where the communication in the field comes in. We can explain things, we can correct things, we can change direction. Construction, generally following best practice procedures. These come from the rules and from standards for water well construction and understanding of good practice. These were, many of the good practice standards were developed in the 1970s by highly experienced people of the National Groundwater Association. Preventive design. For example, these are well screens, not that you could tell by looking at it from this picture, but it's a very fine well screen. Do you need such a very fine well screen for formation, or is it excessively fine and going to cause clogging too soon? Generally with well screen, when you need well screen is you want as much open area as possible. The filter pack should be round and less angular. This is getting more difficult to find. We're starting to work on, there's starting to be a movement toward using round glass or ceramic beads in place of more and more difficult to find round glacially modified filter pack that we used to rely on in North America. In Tanzania, we have a lot of volcanic glass that's available, and that's kind of a neat thing to use. Is the screen even necessary? Many rock boreholes can be constructed with without a screen, but generally use it if there's any possibility of collapse whatsoever. Modern standards. Follow the modern standards, and it's going to help you a lot. Always with water, using clean, disinfected water, filtered as necessary. Never use surface water out of ponds, lakes, streams, anything like that without filtration and modification. If it's a mud drilling program, it has to be high quality drilling fluid products. Typically, sodium bentonite has to be sodium bentonite, not other products. Polymers that are for the drinking water purpose, and as little as biologically active as possible. No biodegradable or phosphorus containing fluid products. With air drilling, the air should be filtered, should not have oil in it. Keeping the pipe and anything going downhole clean and up off the ground. This is going to be a water supply, and you need to keep it clean. Afterwards, because you always make a mess when you're drilling, grinding up rock, moving it around, everything has to be developed thoroughly afterwards. Energy put to it to clean up the formation and bring out all the fines and the dirt. Post-construction, development, looking at it specifically, there are standards for it. Generally, it's a turbidity or sediment content, usually until the water is free of turbidity and sediment. But beyond that, you look at for well efficiency. Usually, development goes until most of the effects of drilling are removed and the well has a good connection with the aquifer, which you can determine by testing. Post-construction development, it reduces the impacts from drilling and well construction on the aquifer, restoring that original permeability, what you were looking for in the first place, and improves the connection with the well. Just conceptually, a poorly developed well might look like this, with the screen being impaired by mud left out in the formation. This impedes intake flow. It also reacts with water constituents to make a poor quality water situation or accelerate clogging. The screen does not operate as theoretically designed, more velocity, more constricted flow. This is, again, conceptually, it's probably never going to look like this exactly, but this is what a properly developed well screen should look like. The top of the well needs to be sanitary and secure. Sanitary and secure, there's several ways of doing this. With a well house, well houses are sources of both comfort and frustration. They can be, they're good for protecting the stuff that's inside, but they can also impair safety. They can cause problems. The wells areas should be fenced, but should have crane access and rooms so the wells can be serviced properly. There should be overhead building access, and there should be a line of sight from the crane to the casing top inside, and room to work inside so it's safe for crews to work. Now, a lot of cranes now have remote operator capability, but still that line of sight makes a big difference. Towers and valve pits, both of these should be set up so that wells can be serviced easily and properly, and the well pits kept clean and sanitary and not flooding with water. We've seen various things, like well pits, like well houses like this, where you have to get on ladders and crawl in over sharp steel and with electrical stuff everywhere, and you don't want to do that. wells that are way too close together, just all kinds of stuff. You can make your own. You can make your own. Drawdown on a pump well. Drawdown has two components. The aquifer losses, well, these are depends on several ways of describing it. Aquifer losses are head losses that occur in the aquifer where the flow is laminar, and they vary linearly with the well discharge. So sometimes they're also called linear well losses. Well losses are aquifer damage that happen during construction. Typically, this usually the component caused by turbulent friction loss, and these are nonlinear or geometric. So there's various ways of describing them, but there are two parts to it. It's basically right at the screen and more associated with the aquifer. Well efficiency. And this should be a main concern to a major water producer or anyone interested in energy construction. When you have poor efficiency, you have increased power consumption for pumping. You have a greater wash zone for biofouling and more likely rehab costs, less available drawdown and a screen, especially with the shallower wells and lower specific capacity. Now, how do we test wells for well and aquifer performance analysis? This is one way to do it. We're using an orifice weir and pumping. Rig testing basically has several components. Rig testing for preliminary analysis, step testing to establish properties, and long-term constant rate tests to delineate the aquifer scale hydrology. The methods for doing this have been around for decades. They're well established. The mathematics is described. The tools are well described. This is one of those things where it really is necessary to do it by the book and do it right and not cut corners. To this, we then add much more recently developed biological and physical chemical water quality methods that help you give the whole picture. Finally, we can look at visual assessments of sediment and debris that come up during these particular components and methods. Specific capacity is often used to describe how a well is performing, but it's not the whole story. The step drawdown test analysis determines those well loss and aquifer loss components. And basically what you're looking at is the shallower the slope and the lower the intercept with the B-axis over here, that's what you're looking for. So more shallow, lower. If it's steeper and higher, then you have those intercepts are less favorable. We can analyze constant rate pumping tests to give aquifer scale properties, and there's several ways of doing this, either by graphical analysis such as this, or using a computer program that spits out the information such as transmissivity. Now, there are many controls on aquifer, on well yield and specific capacity. Aquifer transmissivity, if it's confined or not, then if transmissivity fluctuates, so the specific capacity. If the aquifer is being dewatered, transmissivity and specific capacity decline. So it could be, the well could be squeaky clean, but still be losing specific capacity. You might be looking at issues of construction and clogging and other attempts to reverse clogging. The step drawdown test helps the operator determine if the drilling contractor met specifications, plan that pump design and pump setting, choose an efficient or sustainable pumping rate, and provide a baseline for monitoring performance changes. The well test essentials: accurate flow measurement, for example, with an orifice weir, which is a versatile and accurate way of doing it if they're designed properly. Water level, manual water level tapes and water recorders, especially for those long-term tests. Water quality analysis, and we contend that you should have an actual hydrogeologist present for the test. Accurate water level measurement. The flow rate is known and controlled. The static water level before pumping was started was recorded. The pumping and dynamic water levels are recorded at the correct times by the book, basically on a logarithmic schedule. That is, a lot more often at the beginning and less often later. You have a valid water level tape. It can be in 1/100ths of a feet or in millimeters and meters. A measuring point that is consistently used and known. Let's think about wells, for example, and what we're really wondering about. Basically our view is you're looking at wells and aquifers as assets requiring planning and management. And they're not just a mystery out on a hill somewhere. Wells are the wild engineered interface. You have limited access to a well, there's limited feedback, but there's a lot you don't control in the wild well environment. So you have to do testing to determine what's going on out there. Other challenges: environmental challenges, physical, chemical challenges, just of the groundwater that nature gives you, hydrogeologic issues that nature gives you. Wells tend to be difficult and expensive to replace. Most places can't afford not to plan for sustainability. You must be sustainable, particularly in the modern age. You can't just go over and find more land and drill like you used to maybe in the 70s or 80s. Back then, it was endless horizon. You could buy cornfield for $2,000 an acre and so on, but now they make a lot more money growing corn than they do selling it to you, and they don't want to sell it to you. The same thing with more and more crowded situations. There's just less land available for that. Asset management. What is asset management? It's a process for maintaining a desired level of customer service at the best and appropriate cost. That's one way of looking at it. Similar ideas are stewardship, taking care of whatever it is and it'll take care of you, conservation of resources, and generally responsibility in general. It used to be that many well owners just avoided problems or dealt with them when they came. But that's not the case anymore, hopefully, or less and less. Lots of things can happen in a well. You can have poor original design, poor original development. The water quality may be challenging. There's biological growth. And these affect all these things that in well performance. And they can be analyzed, though. Microorganisms are everywhere. It used to be back early in my career that people used to think aquifers were sterile, but that's been demonstrated to be nothing of the sort. Microorganisms everywhere. Some of them like to clog our wells. There's not much keeping bacteria from moving in the earth. Generally, what causes clogging are changes in redox potentials and minerals. And vast majority of it is iron and manganese. When these two oxidize, they become insoluble and cause clogging. Reducing, if there's presence of sulfide, iron can be reduced and actually become black, and that also clogs. Here's just some of the pretty things that we pull out of wells. Typically what happens with water utilities or anything is that they don't necessarily have a fully developed maintenance program or asset management to begin with, but it can be picked up at any one time. You know, understanding that deterioration can occur, can be slowed and prevented. There has to be institutional commitment, not just one enthusiast, which gets everybody started and then they retire or move on and everything follows. There should be a written but flexible plan to follow, just like any asset management plan. And there has to be training so that it isn't followed blindly. Commitment of everyone involved with the utility is really, really important. Source water protection is part of that. Source water protection protects the overall water quality and make sure you don't get things contaminated. And it's just an integral part of asset management. Understanding where your water comes from, doing the risk assessment, doing the management plan to keep it clean. It's necessary negotiation with things like oil and gas producers or the DNR or others who want to go ahead and say they can put an oil and gas well right in the middle of your well field. They must be technically rigorous to survive these negotiations. Be serious about your well field and defend it. It's your water supply. Don't let them put a oil and gas pad with 300 feet away from your water supply well. Literally, this is asset management. And you need, as part of that, there needs to be regular active water quality monitoring. Think about it. What can go wrong? Swap delineations are done by modeling flow toward wells and then basically making a management product out of it. Plant automation and plant intelligence. Do you have abundant data? How are you going to use it? How do you get your information? Usually we're working with fewer and fewer people, but modern automation allows us to do things with that information and still know what you have to do. Use the information. You don't have to guess. You can know your costs. You know all these other factors. If you keep good records, it gives you good trend lines. Know your benefits as well as your costs. We would like to see you focus on life cycle cost instead of initial cost. And life cycle costs use the cost of design, construction, renewal, replacement, and so on. Do the math, but best to keep what you have in good place, good shape, better than letting it break down and start over. Let's see, better ways to evaluate systems. That's one of the things that we've been identifying. Continuous monitoring that doesn't depend on human sampling. It's the kind of thing that can potentially be done year round, catches events between sampling events. Might have a limited range of parameters, but say something like conductivity will tell you that something bad this way comes and trigger alarms and follow up. Through playing and monitoring and education, it's possible to provide high water quality without elaborate treatment. We've seen this in Slovenia, in landscapes that were occupied since Roman times. We see it in the Russian River Valley of California, where they have big granite collectors and no water treatment program, and it's safe water. This could be your future. Okay, quick summary. Protect your assets. Plan and design wells scientifically. Plan it all based on life cycle valuation. Construct in a quality fashion. Know the deteriorating factors and rates. Practice preventive design maintenance. And that's about it for now. I've got time. You can get at me at the contacts provided, and hopefully you'll learn from all this. We can do this kind of instruction on a large scale for 5.5, 6 hours till I get tired at your place of choice and possibly even online. Thanks for your attention.